In the last module, we had several practice problems. Let's take a look at the solutions to those. A 4 to 20 milliamp PLC output is controlling the 0 to 60 Hz speed reference for a variable frequency drive. When the PLC output is 12.3 milliamps, what frequency output should the VFD send to the motor? As usual, we start off by calculating the slope. In this case, 60 Hz minus 0 Hz for the scaled range, divided by 20 milliamps minus 4 milliamps for the original range. That gives us 60 Hz divided by 16 milliamps, or 3.75 Hz per milliamp. For the y-intercept, we have a scaled minimum value of 0 Hz. So the contribution to the y-intercept from the scaled minimum is 0. When we multiply the original minimum of 4 milliamps by the slope of 3.75 Hz per milliamp, that gives us a contribution from the original minimum of negative 15 Hz. Putting this all together, we have a final equation of y equals 3.75 Hz per milliamp multiplied by x minus 15 Hz. When x is equal to 12.3 milliamps, that gives us 3.75 Hz per milliamp multiplied by 12.3 milliamps minus 15 Hz. The milliamp units from x will cancel with the milliamp units in the denominator of the slope, leaving us with a final unit of measurement of Hertz. In this solution, 31.125 Hz, a little over 50%. Solution number 2. A 0 to 100% PLC variable is controlling a 4 to 20 milliamp output. When the variable is 25%, what loop current should the output produce? Slope in this case is 20 milliamps minus 4 milliamps for the scaled range, divided by 100% minus 0% for the original range, which is equal to 16 milliamps divided by 100%, or 0.16 milliamps per percent. The y-intercept receives a 4 milliamp contribution from the scaled minimum. The original minimum is 0 and does not contribute. Our y-intercept is 4 milliamps. The complete equation for our conversion is y equals 0.16 milliamps per percent multiplied by x plus 4 milliamps. When x is equal to 25%, y is equal to 0.16 milliamps per percent multiplied by 25% plus 4 milliamps. The percent in the numerator of x and the denominator of the slope again cancel. That leaves us with a final solution of 8 milliamps. Solution number 3. A 1 to 5 volt PLC analog input signal is measured by the PLC as a 3,277 to 16,384 integer value. When the PLC input receives 4.17 volts, what raw value should the PLC input value be? We calculate the slope, rise over run, as 16,384 raw value minus 3,277 raw value for the scaled range, divided by 5 volts minus 1 volt for the original range, or 13,107 raw value for every 4 volts, which is equal to 3,276.75 raw value for each volt. We're working with integers, so I'm going to round this to 3,277 raw value per volt. We'll verify a little later that that makes a very small contribution to error. This shows us a very interesting case with our y-intercept, because our y-intercept is equal to a contribution from the scaled minimum of 3,277 raw value minus the contribution from the original minimum which is also 3,277 raw value. We've looked at several of these conversions, and this one is curious because we can clearly see on the graph that we have contribution from both the scaled minimum and the original minimum, and yet we find a y-intercept value of 0. So then the question is, why? The answer lies in the origin of our scaled range values. In reality, we're measuring a 0 to 10 volt signal, and that signal starts at a raw value of 0 when the voltage starts at 0. In other words, if we were to extend our line down to the left, it would cross through the origin point. This gives us an equation of y equals 3,277 raw value for each volt. Plugging in our x of 4.17 volts, we get 3,277 multiplied by 4.17 for a final solution of 13,665 raw value. As I promised earlier, we'll take a look at the amount of error we might have calculated into this by rounding off our slope to an even 3,277 rather than sticking with our original calculation of 3,276 3/4. The difference is about 1 in the raw value, which in this case would be 305 microvolts, about 0.07% error. Solution number 4, a 4 to 20 milliamp signal was being measured by a 0 to 10 volt input card by running the current loop through a 250 ohm precision resistor. The engineer decided to change the resistor value to 500 ohms in order to increase the signal resolution. Part A, what voltage range will be produced at the input card? We solve this using Ohm's law. So we multiply 4 milliamps times the 500 ohms to get 2 volts, and we multiply 20 milliamps by the 500 ohms to get 10 volts. That gives us a range of 2 to 10 volts to represent our 4 to 20 milliamp signal. It would be important here to make sure that this 500 ohm resistor is also a precision resistor. Any error from the tolerance in the resistor could push the upper end beyond the 10 volts that we're set up to be able to measure. Part B, what are the potential drawbacks of doubling the loop resistor value? Increased loop resistance will decrease potential loop length and the number of inputs that can be in the loop. So our ability to push current through the current loop is affected by the total loop resistance. Part C, what influence does changing the resistor have on the measurement resolution? Without establishing a particular input card and knowing the bit resolution, such as a 12-bit or a 16-bit card, etc., we won't be able to define an exact resolution. But resolution ranges are linear, and so we can make a comparison of the ratio of how much resolution we would have in contrast to how much resolution we started with. By dividing the signal range of the 500 ohm resistor by the signal range of the 250 ohm resistor, we see that we have a ratio of 2, so we have twice the resolution that we would have with the original circuit. In some cases, this increased resolution might give us finer PID control or other process control advantages. 250 ohm resistors are the typical choice. However, we do have options that allow us to tailor to our needs.